Question 8. In the Geiger-Marson experiment, alpha particles are scattered by gold nuclei. The experimental results provide evidence that, okay, this shouldn't be any problem. It's B, that most of the mass and positive charge of an atom is concentrated in a small volume. This obviously is the nucleus. The nucleus of the atom is high density, very high density. All the mass basically is there, and all the positive charge. We have the electrons moving around the nucleus. Question 9. It says a radioactive isotope has an activity of 400 BQ. This is Becquerel, and a half-life of 8 days. After 32 days, the activity of the sample is. Okay, so we need to work out how many half-lives there are in 32 days. Well, that's pretty straightforward. So we go 8 days, 16 days, 24 days, 32 days. So you've got 4 half-lives. Each time your activity is going to decrease by a half. It's going to halve. So we're starting off at 400. So after the first one, the first 8 days, you're going to be at 200. It's going to halve again to 100. Going to halve again to 50. It's going to halve again to 25. So there we have it here. Question 10. It says, which of the following decay sequences would result in the daughter nucleus having the same proton number as the parent nucleus? So we're looking at proton number. So basically the number of positive charges in the nucleus is going to be the same. Now let's just think of the ones that we have. We have alpha decay, which is 2 plus, that's 2 protons and 2 neutrons, giving your atomic mass number of 4. So that actually leads, that leads to the proton number, the Z number, decreasing by 2, because it takes out 2 protons from the nucleus. So this definitely wouldn't be correct. Now, what about beta decay? Well, what happens with beta decay, where beta decay comes from, we have a neutron, and what happens, you form a proton plus an electron, which is your beta minus. Now you see here we have your conservation of charge. You've got your positive and negative, which together gives you a neutral. But what actually happens here is your beta decay causes your proton number, your Z number, to increase by 1. So this would just beta decay by itself wouldn't help. The gamma decay is when a light ray is emitted, a high energy light ray, got very high energy, high frequency, but that just causes the total energy of the nucleus to decrease, and so therefore become more stable. It doesn't affect the number of protons or number of electrons. What about this one? Alpha decay followed by beta and then followed by beta. Well, the alpha decay is going to cause the proton number to decrease by 2, but then you're going to have a beta decay and a beta decay. Each one of those is going to cause it to increase by 1, another one by 2. So it would be 2. So this one over here would lead to your number of protons staying the same. And then question 11. It says the difference between the mass of a carbon-12 6, this is carbon-12 6 nucleus, and the sum of the masses of the individual nucleons is 0.1 U. So this is, if you've got this, it means that you've separated all your, you've got 12 protons and neutrons, 6 protons, 6 neutrons. If you separate them all apart, the total mass, the sum of the masses is that there's going to be a difference of 0.1 U. Now this all goes into the binding energy. So which of the following is approximately the binding energy of the nucleus? We're talking about the nucleus as a whole, not per nucleon. So if we look here, we have got our atomic mass unit has got 931 mega eV. That is the energy. Remember, the C to the minus 1, C to the minus 2 is purely just converting that into a mass unit. So we don't need that. This is your energy unit over here. And so we got that as 0.1, so it's going to be a tenth of that, so that's 93.1 mega eV. So this one over here would be about the correct one, 90 mega eV.